Hello everyone, Dr. Zia Tahir here. This tutorial is about 2D heat transfer analysis in Abaqus 2020 and steady state heat transfer through a composite wall. This is problem description. So it contains a composite wall which contains three. Uh, One is a plaster bar on the inside, then a fiberglass insulation, and then a plywood. Plaster wall is 2.5 centimeter, fiberglass insulation is 9 centimeter, plywood is 1.25 centimeter. Thermal conductivity of plaster wall is 0.20. Thermal conductivity of fiberglass is 0.038 and thermal conductivity of plywood is 0.12. The inside room air is at 20 degrees Celsius with a convection coefficient of 10 watt per meter and the outside air is minus 20 with uh, convective heat transfer coefficient of 20. So, and then need to determine temperature at inner and outer surfaces and at interfaces and determine rate of heat transfer through the wall. So, to solve this problem in Abaqus, the height is assumed as 20 centimeter. This is problem 13.10 or the modified version of that from chapter 13, heat transfer and mass transport from the book A First Course in Finite Element Method. So the first step in Abaqus is the modeling, then the second one is analysis, and then the third one is visualize results. So in this video tutorial, I am going to use Abaqus 2020 and the same steps can be performed in any older version or newer version. So the first step is before modeling is to check units. So either they are in set 1 or set 2, meter degree Celsius, watt per degree Celsius, watt per meter square per degree Celsius, or in Kelvin. So for heat transfer using convection and conduction, it doesn't make any difference. Like if you are using temperature in degree Celsius and heat transfer and heat transfer rate and thermal conductivity as degree Kelvin because overall equation that use delta T and delta T in degree Celsius and Kelvin is same. But if you are using radiation as well, so then all units should be in as set 2. So in this problem, thermal conductivity is watt per meter per degree Celsius, heat transfer coefficient as watt per meter square per degree Celsius, and then units are in centimeters. So we need to convert those into standard units, which are meters. After checking units, the next step is to set work directory. So here I want to save all that files like as model and outputs in this chapter 13. So I'm going to just copy its link and then paste in here file, set work directory, and that is a work directory is being set. So that is now everything which I'll do that will be saved in that particular directory. So in modeling, the first step is create part, 2D planar deformable shell. So in Abaqus, you can use model tree or module. In module, that is part. So just click on that or double click on this part. So 2D deformable shell and approximate size. Approximate size is almost 2 times of the maximum dimension. So maximum dimension here is 20 centimeter. So let's say approximate size, it is 20 centimeter, and I am going to do that 50 centimeter because I uh, I need units in meters, so it will be 50 into 10 to the raised power minus 2. Now that is viewport. In viewport, it is possible to draw those triangles using connector lines, like using connector lines. That is a one step. You can do that one. Otherwise, it is possible to use coordinates with these create lines with rectangles. So let's say 0, 0, and then the other one are the coordinates of the other vertex. So they are 2.5 e raised power minus 2 and then 200 e raised power minus 2. So that is part is being created. So x coordinate 2.5 centimeter, 2.5 e raised power minus 2, and y is 20 e raised power minus 2. Click enter, and then that is the part created. So that part is created, and it is created on origin. So that is the first part, and done. So that part name is, I'm going to rename that as plaster. Okay, now the second part, same 2D deformable shell, and that is its approximate length. Continue, and this time I'm using a different technique. So to model that fiberglass insulation, it is 9 centimeter by 20 centimeter. So its width is 9 centimeter and height is 20. So for this purpose, I'm going to just draw a random triangle. Okay, and then I'll add its dimension. So that is 9 centimeter. So 9 e raised power minus 2, 9 centimeter, and then this is 20 e raised power minus 2. So that is 20 e raised power minus 2, and that's enter. So the dimensions are 0.09 and 0.02. I can drag that somewhere here. Okay, so that is the second part is fiber. Fiber. And now the third one, in the similar way, 2D deformable shell, 0.5, and its width is, I can use another triangle here. That is a triangle, so add dimension. So that is 1.25 e raised power minus 2, and then its height is 20 e raised power minus 2. Okay, so here are the dimensions, 0.0125 and then 0.2. So done. And now just to this part 3 is I'm going to rename that as ply. So these are the three parts. So let's say fiber, to make sure that everything is okay. Sketch section 0.2, and then that is 0.09. The other one is plaster. Double click on yes, and dimensions are not there, so dimensions can be added. So done, 0.2, and it is rounded to 0.025 is being rounded. So that is done. Done. Okay, so it says that it is, so you just suppress it and then resume it. And then the last one, plywood, in the similar way. So that is a cell section. So done. Okay. So now, so these three parts has been created. The next step is create surfaces, and these are required to apply temperature and convective heat transfer. So it can be done in a later part, but it is better that if you create surfaces and only those surfaces where you need to apply temperature and heat transfer uh, coefficient. So for that one surface is required here on the inside of plaster wall and then one on outside. It means that left of plaster wall and then right of plywood. And surfaces are also required to define a contact between plaster wall and fiberglass insulation and plywood. So right and left surfaces, so they are need to be created for. So to create surface, let's say in the fiber, and here are the surfaces. Okay, so I am using that left and right. So left, it's a continue, and then that is the edge for left. Then another surface need to be created, and that is right. So select that edge and done. So I have created that surfaces for plaster. That is plaster, left surface, right surface, and then similarly for ply, that is left surface and that is right surface. So surfaces have been created. So once surfaces are created, the next one is create datum plane. And why is that datum plane is required? It is to find temperature at specific point, and it will make it easier for find out the nodes. So sometimes you can create partition, but for this particular part, it is optional. So for that purpose, like the first part, and then here tool, datum, datum plane, and midway between 2 points. So I want to create a datum plane midway between these 2 points. And similarly for all other parts, like for plaster, okay, the tools, datum plane midway between these 2 points. Okay, so once datum has been created, the next one is to create material. And in material, it will be thermal and then conductivity, because thermal conductivity is only that what we need. So here in the property module, so that is material, or otherwise here are materials. So like as I have designated plaster as material 1, so thermal conductivity of plaster is zero point 0.2. Then the second one is fiberglass thermal conductivity, and thermal conductivity of that is 0.038. And then the third material is plywood, and for plywood it is 0.12. So here three materials have been created. The first one is uh, that is material 1 is plaster, thermal conductivity 0.2. Second material is fiberglass, thermal conductivity 0.038. And the third one is plywood 0.012. Next step is in the property module, create section and then assign section. So create section and assign section. So we have three parts here. For three parts, we need to create three sections. So section 1 correspond to plaster wall because I have designated that as 1. So continue, and then for that one material 1. Then the second section, solid homogeneous, continue, and then it is material 2. And then for the third section, solid homogeneous, and then material 3. So in the section, you can see that section 1 is being created, that corresponds to material 1, then section 2, then section 3. Okay, so once it's done, then then assign, here is assign section, or you can go here in each one, like for fiber, section assignment. So there is no need to create set, it select the region. So that need to select, done. And fiber is designated at 2, so that is 2. Fiber done, and then plaster. So section assignment, select the region, and plaster is designated as 1. So here the section is 1 for that. And then ply, section assignment, and then here done, and that is for ply, it is 3. Like as here you can see plaster wall I have designated as 1, fiberglass as 2, and plywood as 3. Next step is in the mesh module, seed part, assign mesh controls, mesh part, and then assign element type. So this need to be performed for all the parts. Okay. So depending upon like which computer you have, so you can either use Finder mesh or a curse mesh for that. So for that purpose, here in the mesh, okay, model, and then the first one, like, okay, supply, and then plaster or a fiber, so anything like that. Okay, so that is a here is the seed part. Seed part, so double click on that, and it is approximate global size of that. So I am using here as 0.25 centimeter, so 0.25 e raised per minus 2. So this is the one which I have to use for all. So it's better that global size, so keep that same for all. So 0.25 centimeters, so it is 0.25 into 10 to the raise per minus 2. So apply that is, and then assign mesh controls. So for that is quadratic mesh and free, and then algorithm is medial axis. Okay, then this one mesh part, yes, and then here assign element type, and element type in the family is heat transfer, standard linear, and then DC to D4. So that is the material type, like family, heat transfer, and then DC to D4. So that is element type. Okay, so now that mesh has been done. Similarly for the plaster. So it's again 0.25 apply. Okay, assign mesh control. That is quadratic. The same one. Then yes. Then assign here in the family. It is heat transfer. Okay, and element type is DC to D4. After plaster, it is done, and then fiber. So the same one, 0.025 apply. Okay, mesh control quadratic, free, and medial axis. Yes, then here you have heat transfer family. So now the mesh of all these fiber, plaster, and then ply, so that for all those the mesh is done. So in the part, a set is required and node type is required, like create set and then node type. So in for each part, set is required. Okay. So like, why is that required? Because temperature at the interface or the surfaces is required, and then because the datum is created at the middle of each part, so left node and right node for each part is need to select. So here is the node, and I am going to say it as left node. Continue, and that is the left node. And another set, I'm going to name it as right node, and then type is node. Continue, and then that one is done. So I've created for plaster as well, like as this is a left node for plaster, right node for plaster, and then that is the left node for ply and right node for ply. And similarly for fiber, that is left node and that is right node. So next step is in assembly, create instance and then to translate instance. So here in the assembly module, create instance. So I'm going to select all these. Okay, so now these are the three instances or three parts in the assembly. So now need to translate them as they were in the problem. So plaster wall is on left, fiberglass insulation in the middle, and plywood on right. So then translate instance, here you have option of translate instance. So I'm going to keep that middle as where is it? So translate, this one is translate instance. It says select the instance to translate. I want to translate that one, selected. And then select an axis or start point of the translation. So that is the start point. I want to move that point here, and then you can see it is being moved. So that is done. Okay, again it says select the instance to translate. Now I want to translate plywood, and then the starting point is here. Okay, and that is the end point there. So okay, and that is done. Now I can see the part. So three parts, they are now translated. So in the assembly module, I can check if they are rightly placed. So that is fiber in the middle, plaster on the left, and ply on the right. So this is how we are going to assemble different parts. So next step is to create step, and it is heat transfer and steady state. So for that one, here you have step module, and then this one is create step. So step is, I am going to name it as heat transfer. Okay, and here I'm going to select heat transfer, continue, and then here you have steady state response. And the time period for that, by default, it is 1 second. So I am going to use that as 1 second. Okay, so now step has been created. Next step is to, in interaction module, create strain, and the tie strain is required to define contact between the two edges. So here I want to develop a tie contact between that plaster wall and fiberglass, and then fiberglass and plywood. So in the interaction module, here is constraint. So create constraint, and that constraint one I am going to name it, and that is tie. Okay, so continue. It say select the master type surface. So I have already created that, and the master it is usually the direction of heat flow. Okay, so surface, and here is the surfaces, and that is plaster wall right surface. So that is the plaster right surface, that is a master, and then slave surface, and slave surface is fiberglass left. So that is fiberglass left. Continue, and here you can see that both surfaces are being highlighted, although because they are overlapping, so both are being highlighted here. Okay, so then you can see, and similarly the other contact is here, and surface for that one, for fiberglass it's right, fiberglass right, and then slave surfaces, plywood left. So ply left, and you can see highlighted surfaces, and then that here you can see that constraint 1, and that is a constraint 2. So both constraints are being developed there. Next step is to create interactions, and the interactions are surface film condition to apply temperature and coefficient of heat transfer. So here are interactions, or otherwise they can be created here. That is interaction and intersection. I am going to use that inside. Step is heat transfer, surface film condition, and then for the inside wall, so it says that which one is it. So plaster left is inside, continue, and film coefficient. So for inside wall, it is 10 heat transfer coefficient, and the temperature is 20 for inside. And you can see here interaction is being created, the other one here. So I can name it as outside, surface film condition, and outside is plywood right. So plywood right, and for outside it is 20, and then temperature is minus 20. Okay, so now interactions have been. So now the model part is done. Once model part is done, then you need to go to job, create job, perform data check, and submit. So I am going to model that, rename that model 1 as, rename as composite wall. That is the model. And then I'm going here, double click here, create a job composite wall, and then continue. So that is job created here. Once job is being created, apply data check. So it's a history output is not requested in the following step. So no need of it. So it is being submitted, check submitted. It will take some time to run, and then check running. So now the data check is completed. So once it's being completed, so then need to submit that job. Okay, so it is being submitted. It will take a few minutes, or depending upon the computing it's running, and then it will take some time to complete. So job is completed, and then once job is completed, so then that analysis is done. So the next is results, and to get results, so you can right click here and then go to the results, or otherwise file, open, and then ODB file. So that is a composite file. Okay, so that is now you got, and then here the deformed shape you can visualize, that is the temperature gradient, that is the heat flux is a constant, and that is a nodal temperature, and then so nodal temperature. So for visualization, we need to plot XY data from ODB field out. Temperature at inner and outer surfaces. So that is the inner, that is outer surface. And then at the interface is required. and determine the rate of heat transfer through the wall. So I have created node there, like on inner surface, at interface, at outer surface, and then interface, because we have developed a tie contact, so the temperature at that contact will be the same. So for visualization, plot XY data and then ODB field output. And for that purpose, so here you have create XY data in the visualization and ODB field output. So now variable is unique node here for unique node, and then that is a heat flux, but I'm interested in the nodal temperature. Nodal temperature at what? And for that one, I'll go into the nodes. I have created node set. So for that one, so first inside, that is the plaster wall, and that is the left node. Okay, so that will be inside. So I am going to plot that one. So this is temperature at inside, and you can see that it is going to at 1 second, and that is the maximum value of temperature 18.54. And then on inside is the plywood right node plot, and that is a minus 19. And then uh, plaster wall right node, that is the interface, and that is plaster wall, so that is temperature at one interface, that is between fiberglass insulation and plywood. And then the other one for plaster wall right node, and that is the other interface, temperature is 16.72. So those are the values of uh, temperature, and then I can save those values. And then the heat flux magnitude I'm going for, just for heat flux magnitude on these nodes, and that is the heat flux is 14.55. Okay, or otherwise I can go in the deform shape, and then I can see that heat flux is 14.558. That is the heat flux uh, for because the steady state and heat flux is constant for that one. So that problem is being solved. So temperature at the like along that each node that is being computed, and then rate of heat transfer is being determined. So I hope that you find this video tutorial helpful for you. Thank you very much for watching. So you can leave feedback as comments.